So if there's any work in your folder that has a check mark on it, you can take it out, and if you want to turn anything in, just put it in your folder. Today's class 5. We're going to talk about the derivative function and differentiability. Our first quiz is going to come up next week, right? So Friday of next week, I'll give you your first take-home quiz, and that's a project check-in day. The more you have, more work you've done on the 2 projects by that day, the more productive that day is going to be for you, right? The more helpful it's going to be able to come in with things that you're working on, prepared to discuss with your classmates and ask questions. So think about that over the weekend. Maybe dig into those projects a little bit. Okay. In this class, we're going to sketch the graph of the derivative function given a graph, and we also explore what kinds of things make functions non-differentiable. So in the last section, we defined the derivative of a function f at some x value a to be f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay, so if you ignore the limit, this difference quotient, it's called, represents the slope of a secant line between the point a, comma, f of a, and a plus h, comma, f of a plus h. So that represents the slope of a secant line. And then you let h go to 0, h being the distance between the 2 x coordinates of your points. Okay, so that thing approaches a tangent line. So since you can find f prime of a for every number a, you can pick any number at all and you can find the derivative of the function at that point. So at any point on the graph, you can draw a tangent line and find its slope. So that means we can view f prime of x as a function of itself, another function, f prime of x. So that means for each input x, there is exactly one output that represents the slope of the tangent line of f at that point. So the limit definition of the derivative of the function f of x at any given x value is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So it's exactly like what we did last class, right? But last class a was representing some, like a number, like 2, right? And we were calculating the slope of the tangent line at 2. Now we're saying we can let that point vary. We could do this calculation at any x value. So instead of a's, we put x's, because x is going to be a variable now. Yeah. So a was representing a constant, and now x is representing a variable. So let's see if we can take the graph of f of x pictured below and sketch the graph of f prime, graph of the derivative function. Okay, so the basic idea when you're trying to graph the derivative function is to plot points that are x, comma, slope of a tangent line. Okay, so if this is f of x, this one on the left is f of x, I want to plot x, comma, the slope of the tangent line at that x value. So are there any x values in this picture that have really easy to calculate tangent line slopes? The flat spots, yeah. So right here, and right here, you have horizontal tangent lines. Horizontal tangent lines have slope of 0. So I'm going to plot for an x value of -1, I don't know, like 1.5-ish, and 1 1/3, and 3. I'm going to plot zeros on my derivative function f prime, right? Because we're plotting the x value, comma, the slope of the tangent line. So -1 gets a 0, about 1 1/3 gets a 0, and about 3 gets a 0. So those are the places where the derivative is 0. Slope of the tangent line is 0. All right, so let's look to the left of -1. The slopes to the left of -1 at every tangent line, I like to kind of use my hand as a tangent line, and I lay it along the curve to picture what's happening to the tangent lines. You can also just draw a few, right? Here's a few tangent lines. The slopes of those tangent lines, are they positive or negative? Negative. And as I get further away from -1, right, they get steeper and steeper and steeper. So they are getting more and more and more negative. So they're negative and they're getting more and more negative. All right. Between -1 and 1 1/3, say, the place between the next two places that it's 0, the slopes are positive. You can draw a few, right? Positive, positive, positive. Those are all positive, right? Because they're increasing lines. Okay, so it starts at 0 and it gets more and more and more positive until it hits 0, and then it stays positive, but it starts coming back down towards flat. Starts coming back towards 0. Okay, so it gets more and more positive until it hits 0, and then it starts coming back down. No. No, and when you're sketching a derivative function, they're very rough sketches. It's hard to tell exactly how fast the derivative is changing from a picture. So yeah, so what Alex is suggesting is maybe it goes fast near the 0 and then kind of flattens out like that. Yeah, that's actually not what happens, but it is very hard to tell that that's not the case from the picture. Something like that. We also can't tell exactly how high this thing goes, right? It's hard to estimate exactly what the slope is of the tangent line just by drawing a picture. So this is a qualitative picture. It's not perfect. Okay, so now between the next two horizontal tangent lines, I want to analyze the tangent lines in between there. So I draw a couple, and they are negative. So it starts at 0, gets negative, more and more negative, until, I don't know, maybe about there. Maybe about right there. And then it stays negative, but starts getting flatter again. Starts coming back towards 0. So it gets negative, hits some minimum, the most negative or the steepest point, and then starts coming back up until it becomes horizontal again. The slope of the tangent line is 0. Okay, and then after this spot, draw a few tangent lines. What are their slopes, positive or negative? Positive, and they start at 0 and they get steeper and steeper and steeper and steeper. So they just become more and more and more positive. So it looks something like that. Yeah, so if these two graphs represented polynomials, what would the smallest degree of f of x have to be? Think about the end behavior. If the end behavior is both arms up, the degree has to be even, right? So this could be degree 4. This is maybe a degree 4 polynomial. I mean, that's not for sure, but it looks like a degree 4 polynomial. And what does its derivative look like? A cubic. Yeah, this could be a degree 3 polynomial. We're going to see in a few days that that's actually a rule that happens when you take the derivative of a polynomial. The degree is going to decrease by 1 in the derivative. Oops. All right, so we're going to come back together with about 30 minutes remaining in class for another little demo. But in the meantime, you are going to work on some group activities, drawing graphs for functions. For B, it says use algebra and the definition of the derivative to find a formula for the derivative. Don't do that. That's going to just take too long. So a function is said to be differentiable if its derivative, f prime of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h exists. Okay, so a function is differentiable if that limit exists. So we've seen a few ways for a limit to fail to exist. Here are the basic ways that a derivative can fail to exist. You can have a corner. So it's hard to decide how to draw a tangent line at a corner, because the limit from the left, if you start drawing tangent lines from the left, it looks like that would be the tangent line. But if you start drawing tangent lines from the right, it looks like that would be the tangent line. And right at the point, like, how do you draw a tangent line on a corner? It's not well defined, right? So we say it's not differentiable there. So whenever you have a corner, the function is not differentiable. A vertical tangent line is a place that's not differentiable because the slope of that tangent line is what? A vertical line has an undefined slope. Yeah. So the derivative would have to be undefined because the derivative represents the slope of the tangent line, and the slope of a vertical line is undefined. And then if we have a discontinuity, you can't take the derivative there, because you can't draw a tangent line at a point that doesn't exist. Yes. You could take the derivative very close, yeah. And you could say, in a point discontinuity like this one, you could say, well, if I just filled it in, like, you could figure out what the slope would be if you filled it in. But if it doesn't live there, you can't draw a tangent line. Any vertical tangent line, the derivative doesn't exist just at that point. So in this particular case, you know, let's say that's a 3. You would say f prime of 3 is undefined. You can draw a derivative in anywhere else. Anywhere else you can draw a tangent line and calculate its slope. Just at that one point, you say the function's not differentiable.
But you could still have f prime of x.
Yes, you could still come up with an f prime of x function, and you would just say that the domain of that function is all x values except for 3. So, for example, in the algebra problem that you did a little earlier, this one, you came up with f prime of x was 1 over 2 square roots of x. The domain of that function, you can't plug a 0 in for x, right? That's because when you graph the square root of x, the original function, what do you have right here? So for a derivative. Yeah, you can't define a derivative here because that's like a corner, right? It's just like it stops. So it's like right, which makes it undefined. Yeah. So graphically it's undefined because this is a corner. Algebraically it's undefined because you can't put 0 into that function. Yeah. So something similar would happen if I had a formula for f prime of x for this curve with the vertical tangent line. There would be some reason you couldn't plug x into it. You'd get a 0 in a denominator or something. X minus 3 or something would be in the denominator, yeah. So points of non-differentiability for each of these functions. So this is the greatest integer function. It means whatever you plug in, you round it down to the integer below. So from 0 up until 1, you round down, right? So if I plug in 0.8, you round it down to 0, right? Even though that thing's above 0.5 and the standard rounding rules would say round up, this function says round everything down. So if I plug in anything between 1 and 2, like 1.5, you round it down to 1. So your function looks like this. So it's discontinuous at every integer, right? It has a discontinuity at every integer, and discontinuities are places where a function is not differentiable. Because how do I draw a tangent line at, say, right there? right? I could draw that line or that line or that line. It's hard to say which one would be a tangent line. So this is not differentiable at every integer because it's discontinuous at those integers. Can't take a derivative. Yeah, not because that's a piecewise function. There isn't a clean algebra that goes with it. Yes.
Not all piecewise functions are.
True. Yes. Not all piecewise functions. Certainly not. Yeah. They often have discontinuities. They often have corners, but not always. Okay. So the fifth root of x. Is there a place in the fifth root of x graph where you can't take a derivative? X equals 0 because you have a vertical tangent line. Not differentiable at x equals 0. Okay, here's another piecewise function. So let's remind ourselves how to do this, right? This is like an old skill. I'm supposed to graph the line y equals x when x is less than 3. So that would look something like that. That's the line y equals x. But I only graph that for x is less than 3. I stopped when I got to 3. And then the line 2x minus 3 when x is bigger than or equal to 3. So if you guys, it's fine if you work on something else, but you're distracting everybody with your talking. 2x minus 3, if you plug a 3 in there, you get 3, right? So if I'm graphing the second part of this function, I get 3, and then pick another point like 4. What do you get if you plug 4 into that line? 5. So 4 comma 5 looks like that. Okay, so there's my graph. Does it have any spots in it that you cannot take a derivative? The corner at 3. Yeah. You can't take a derivative at x equals 3 because it's a corner, sharp corner. So we have our 3 ways that a function can fail to be differentiable. A place where it's discontinuous, there's a jump or a hole, a place where the tangent line is vertical, or a place where you have a sharp corner. So a few different ways to speak the language of differentiability. A function is differentiable at x equals 2, or you could just say differentiable at 2. If a function is differentiable on a whole range of points, you can list it as an interval. The function is differentiable at every point between x equals 0 and x equals 5. And if a function is differentiable everywhere, at every possible x value, you can just say the function is differentiable. You're right, I used range colloquially and not in the math terms. I meant it's more of a domain, you're right, because those are x values. Okay, so now I'm going to have you sketch some more derivatives like you were doing earlier, but these derivatives are going to have places where the derivative is undefined. So you're going to have to be a little bit more careful about drawing your graphs. And if the derivative is undefined, make sure you don't plot anything there.